Hi, and welcome to Codex. Our speaker today is Felix Voigtländer, who is the professor for mathematics and reliable machine learning at the Mathematical Institute for Machine Learning and Data Science at KU Eichstätt-Ingolstadt. Dr. Voigtländer works in the mathematics of machine learning, functional analysis, and harmonic analysis. Today, he will tell us about the sampling numbers of Fourier-type Barron spaces. Take it away, Felix.
Yeah, thanks for the introduction. So yeah, and thanks for letting me speak here. Yes, so there was already this slight confusion about the title. So I think I changed it now 2 times, once from one announcement to the next and once from the announcement to the final talk. So the actual title is sampling numbers of the Fourier-analytic Barron spaces. And in the course of the talk, I will explain what these sampling numbers are and actually what these Fourier-analytic Barron spaces are. So as we will see, there are 2 types of Barron spaces in the literature, and I'm only mainly interested in one of them, but I will also briefly, just to make the distinction between the 2 types of Barron spaces clear, go into the other one. So the talk is split into 4 parts. In the first part, I will tell you what these Fourier-analytic Barron spaces are and why they are interesting or why they have been studied a lot. Then in the second part, I will tell you what just abstractly these so-called sampling numbers are. So put short, the question there is, you have an unknown function from some class, so you know which class, but you don't know the function. And then you ask, if I can sample this function at m points, how well can I reconstruct the function? So this is the short summary of these sampling numbers. Then in the third part of the talk, which is actually just 1 slide, I will present the main result, which is upper and lower bounds for these sampling numbers for this Barron space, for this Fourier-analytic Barron space. And then depending on how much time is left, I will go into actually quite a few of the proof ideas because I think they are quite interesting. So this is a mix of techniques from compressive sensing, harmonic analysis, and approximation theory, basically. Okay, so let's start with the Fourier-analytic Barron spaces. So this is, by the way, Fourier, and this is Andrew Barron. And we will somehow meet a space which is at the intersection of the 2 people. So what's the Barron space or the Fourier-analytic Barron space? So I will, in this talk, always be working on this unit cube omega, and for some notational convenience, I don't choose it to be 0, 1 to the d, but minus 1/2 to 1/2 to the d. And I say a function on this cube is a Barron function with smoothness alpha if there exists some function capital F, which you can basically think of as the Fourier transform of the function little f. And this function capital F, the Fourier transform, basically should satisfy 2 things. It should be integrable when you weight it with this factor 1 plus absolute value of xi, so this is the Euclidean norm, to the alpha. And it should be the Fourier transform of f in this sense that if you take the inverse Fourier transform of capital F, you actually do get back f. So why do I make all this fuss about like Fourier transform and quotation marks? Because of course your function f is only defined on the cube and not on all of Rd. And this function capital F is basically you extend the function small f from the cube to all of Rd in a suitable way. Then this extended function has a unique Fourier transform, let's say capital F. And then you can ask, does this capital F satisfy this condition or not? And basically what we are asking is that there is some nice extension of F from the cube to all of Rd such that the Fourier transform satisfies this integrability condition here. And of course, we can extend F in many ways. So to define the norm on this Barron space, this is just the infimum where you take this weighted L1 norm of the Fourier transform of the extension, where you take the infimum over all possible extensions. Yes, or put differently, you take the infimum over all capital F, which satisfy this condition here, where the norm is smallest. And then the most important notation you should remember for the rest of the talk is U alpha of omega is basically the unit ball in this Barron space. So it consists, this should be an in and not a colon. This consists of all F in the Barron space, which have norm less or equal than 1. Okay, now, I mean, this, of course, you can define this thing, but the question is, why is it interesting and why have people studied this space? And the answer is that there is some connection to neural networks. And this was discovered by Barron originally in 1992. So he showed that if you have a function in the unit ball of this Barron space with exponent 1, so this means f of xi is integrable against 1 plus the Euclidean norm of xi. Then you can approximate such a function very well using certain shallow neural networks. So let's maybe first go into what a shallow neural network is. You have some activation function, which in this slide I will mostly pick to be the ReLU function, which just computes the positive part of x. And then a single neuron is a function of the form, you first compute the inner product of x with some weight w. So you compute the inner product wx at some bias b, and then you compose this with the ReLU function. So this is a single neuron, and then in shallow neural networks with capital N neurons, it's just a linear combination of capital N of these single neurons. And what Barron showed basically is that if you have such a function in the unit ball of the exponent 1 Barron space, then for whatever input dimension, you can approximate such a function with a shallow network with N neurons up to error essentially square root of d over n. So this means that basically you can overcome the curse of dimension for this function class. What is the curse of dimension? So usually, or for many function classes, if you want to do something like approximate functions from the function class with n parameters, then you need to get a certain accuracy epsilon, exponentially many parameters, neurons, whatever, exponentially many in the dimension. And this is not the case here, right? So here you always get error square root of d over n. So d only, the input dimension d only enters polynomially and not exponentially. Okay, and so actually Barron showed this for a slightly different thing. He didn't show this for the ReLU function originally, but for the Heaviside function. And then this is why I'm listing myself here and two of my co-authors. We extended this very slightly to actually make it such that you can do it for the ReLU function and such that you can do it with uniformly bounded weights. And the proof of the original result by Barron, where he used the Heaviside activation function, is, I think, very nice. And it also motivates the definition of the second type of Barron functions. And this is why I will now briefly go over the proof. So, okay, what is the Heaviside function? This is just the indicator function of the positive numbers. So it's 1 on the positive numbers and 0 on the negative numbers. And what we want to show or want to see is that you can approximate a function in this Barron unit ball very well by using shallow networks with this activation function. Okay, and the first step is just to assume without loss of generality that f vanishes at the origin. This you can easily do. And what Barron then showed, this is a nice computation, which I will not repeat here, is that since you are in this Barron unit ball, you can actually represent f as an integral over stuff that looks like this. Okay, what's this p? This is just a probability distribution over, or probability density function over rd times 0, 1. What is this term here? This is one single neuron with a Heaviside function, where you put in theta over absolute value of theta as the weight, and t as the bias, or minus t as the bias, and you subtract from that a different neuron. So basically this, what you see here, is a 2-neuron shallow Heaviside network, and this s of theta t is just a scalar between -1 and 1. So what this essentially tells us is that we have written the function f of x at each individual x as an expectation of a shallow Heaviside network with 2 neurons. And then what you can do is you can draw a lot of independent samples and basically use the law of large numbers to get your approximation. So let's draw a lot of samples theta n1 t1 up to theta m from this probability density function here. And then we consider a random Heaviside network with 2 neurons, which is just, you take this full shebang here and everywhere plug in your theta I and your ti. Then this phi I is a random Heaviside neural network with just 2 neurons. And in expectation, just because of this equation here, it exactly gives you f of x at each individual point x. And this thing here is bounded in absolute value by 1, meaning that the variance is also less or equal than 1. And then you can just use a very standard law of large numbers argument. So you take the expectation over the parameters, over these theta I, ti here, and look how far is in the squared L2 norm my average of these random neural networks, how far is it away from f? And then by Fabini, you can pull in the expectation into the integral. This here is then the law of large numbers thing, which, because the variance is always bounded by 1, you can bound by 1 over m. And since the expectation of this full squared error is less than 1 over m, you know that for some realization, the error will be, the squared L2 error will be bounded by 1 over m. Okay, now, so this is a very nice proof, but it has two shortcomings. The first is in the result that I cited in the previous slide, we actually had the Rayleigh activation function, not the Heaviside function. And here we now have L2 approximation and not uniform approximation. And by modifying this proof actually quite heavily because of the L infinity approximation, you can actually also get that. But I found this proof here quite nice, so I wanted to present it. And it also motivates on the next slide a definition of a different type of Barron space. So in addition to these Fourier-analytic Barron spaces that I have been talking about, people have also been considering certain, so what I call infinitely wide Barron spaces. I don't think that many other people use this name, but I like to call them this way, and we will see in a moment why. So let's first look at the infinitely wide Barron space for the Heaviside activation function. We will again always be considering functions on this unit cube. And sigma, this is now our parameter space. This is r times rd times r. Why? Because each neuron has a weight vector, which is from rd. There's a bias, which comes from r. And we can multiply it by a scalar when we take the linear combination, this r part here. And then if we now take the Heaviside activation function, we say that f belongs to this Heaviside infinitely wide Barron space if you can write f as such an integral here, where nu is a probability measure, so we have a distribution on the parameters CWB, such that you can then write f as an integral over basically, or you can write it as an expectation of single neuron networks. And to compute the norm, or the condition that you require from this probability distribution, is that if you just integrate over the absolute value of c, so this thing here, this should be bounded. And the reason why you don't actually in this norm consider b and w is because the Heaviside function is invariant under scaling, right? Heaviside of 1 million x is just Heaviside of x. So it wouldn't make sense to consider how big or how large b and w are. Whereas if you consider the Rayleigh activation function, then you can write the same thing here. You require that f can be written as the expectation of a certain random neural network. And now it's natural to require this condition from the weights because the Rayleigh is one homogeneous, right? So Rayleigh of tx is t Rayleigh of x if t is bigger than 0. And now how does this relate to the Fourier-analytic Barron space? Well, at first they are formally different, or they are formally different, but this definition somehow fits into the scale of the two others. If, as the activation function, you consider the complex exponential, right, e to the ix basically, then this is roughly of the same form as this, essentially, or especially if alpha is equal to 1. And so basically, I only mentioned this now so that if you're interested in these Barron spaces, you know what kind of Barron space I will be talking about in the remainder of the talk. So I will only focus on this Fourier-analytic Barron space. Yeah, so are there any questions up to here? Don't seem so. And then let's introduce the second actor of this talk. These are the sampling numbers. And as I said, the sampling numbers measure how well can you recover an unknown function f from some given function class, curly f, using point samples. So the precise definition is as follows. We again work on the unit cube, and we have some known function class curly f of continuous functions on omega, and we will measure the error in LP for some p. And then the mth nonlinear LP sampling number of this function class curly f is defined as follows. You take the infimum over all possible sampling points, so you are free to place the sampling points anywhere you want. And you take the infimum over all reconstruction operators, so these are arbitrary maps from Rm to LP. And then given the sampling points and the reconstruction operator, you ask what is the worst case reconstruction error over the full class f. So you sample f at f of x1 up to f of xm, put this into the reconstruction operator. This gives you some LP function. And then you ask how far away is this from f? And you take the worst case error over the full class. And what I should mention, so these are the non-linear sampling numbers. So R is really an arbitrary map. It can be non-linear, it can do crazy stuff. We don't really require anything else from it. But there are variants of these sampling numbers. One variant is the linear sampling numbers, where you do actually require the reconstruction operator to be a linear map. And also here, everything is deterministic. You have to choose once the sampling points and the operator. There are also certain randomized sampling numbers, which, because I don't want to write randomized every time, I abbreviate with sigma m MC for Monte Carlo, but this doesn't have to be a Monte Carlo algorithm. It can be any randomized algorithm. So what does this mean? You can choose the sampling points randomly if you want, and also the reconstruction operator R can involve randomness. So it can basically be a random variable. And in this case, you don't consider just the worst case error, but you consider the worst case expected error. So for each F, you ask, in expectation over all the randomness of the sampling points and this reconstruction operator, how big will the reconstruction error be? Okay, so this is the definition. And for classical spaces, this has been studied quite in depth already. So in the information-based complexity community, and just as one sample result in this direction, let's consider the case where curly F is the unit ball of CK, so of K times continuously differentiable functions. And then you can show in whatever LQ space you do your reconstruction, the linear sampling numbers will behave like the randomized sampling numbers will behave like the deterministic nonlinear sampling numbers, and they all behave like m to the minus k over d. As m goes to infinity, d fixed. And what does this mean? This means on the one hand that if the dimension is very large, then your sampling numbers will decay very slowly to 0 as m goes to infinity. On the other hand, if you have very large smoothness, maybe even larger than d, then at least as m goes to infinity, you will have quite a quick decay of the error. But what one should mention is that in this hidden constant here, this really depends also on d. And usually it depends exponentially on d. So this result is really an asymptotic result once m is exponentially large in d. Yes, so this is one standard result. And on the next slide, I just want to show you a warning that in general, there's a difference. I mean, we are always talking about a function class, like the unit ball of CK. And if you have such a function class, you can also ask, how well can I approximate functions in there by polynomials of degree n or by neural networks or whatever? And in general, it is not true that if you can approximate the functions in the class very well, this does in general not imply that you can sample or recover the functions by sampling very well. And just as one example of this class, of this phenomenon, we will look at the following settings. So we look at the set NN L beta, and this is a bit, the definition looks a bit complicated, but it's not so bad in the end. So this L is the number of layers of neural networks that we consider. And then we ask, how well can we approximate this given function by, let's say, Rayleigh neural networks with n weights? So with n non-zero weights, and they should all be bounded by 1. And we allow L minus 1 hidden layers, so L layers in total. And then a function belongs to this class n and L beta if for each n there is a Rayleigh network with at most n weights and L minus 1 hidden layers and all weights bounded by 1, such that you have this approximation error here. So this means if beta is very, very large, you can rapidly approximate your function using just a few non-zero weights. And now we ask the question, how well can you sample or recover such a function from point samples? And this is from a paper with Philip Gross and myself that was appeared on the archive recently. So we show the following. We show our upper and lower bounds for these sampling numbers, but they are not really tight. So we show that they are upper bounded by essentially m to the minus 1/2 beta over 1 plus beta, and lower bounded by this expression here. So you will never be able to do better than this, and you can do this well. And I mean, it all looks a bit confusing at first sight. So what are the take-home messages? The first one is that the exponent here, I mean, the implicit constant depends on D, but the exponent here and here does not depend on D. So this means that you can actually, to some extent, overcome the curse of dimension. But what you should also note is, no matter how big you make this beta, so no matter how rapidly you can approximate your function by neural networks, the approximation or the decay of the sampling numbers is actually, or it saturates. You can never get a better decay than m to the minus 3 over 2. So this here will always be bigger than m to the minus 3 over 2, even if beta is really, really large. The last message is or the next message is, if the depth of the networks is really big, then you will definitely never be able to get a rate better than m to the minus 1/2. And this is all just for L2 recovery. So if you actually want recovery in the uniform norm, then you get this lower bound, meaning that you're then really fully subject to the curse of dimension. So you will never get a better rate than m to the minus 1 over d, even if beta is really, really large. Okay, I mean, if you didn't get the details of this, the main point, as I said, of this slide that I wanted to make is just knowing that you can approximate your functions in your function class very well by something, by polynomials or by neural networks or whatever, does in general not imply that you can recover your functions well from samples. Yeah, now I want to somehow present the main result that I want to talk about in this talk. And the question now is, how well can we recover from point samples functions in this Fourier-analytic Barron class or unit ball of the Barron space? Just as a reminder, so this is the Barron space again. We say a function is in the Barron space if you can write it as the inverse Fourier transform basically of some capital F, where capital F satisfies this condition here. Okay, and what is the bound? The bound says the following. So the deterministic nonlinear sampling numbers are upper bounded up to this log factor by m to the minus 1/2 minus alpha over d. And it's always the case that the randomized sampling numbers are smaller or equal than the deterministic ones, because each deterministic algorithm is also trivially a randomized algorithm. And we can also lower bound these randomized sampling numbers by m to the minus 1/2 plus alpha over d. So this means up to this log factor, we really get a tight bound, the same bound from above and below. But one small, or maybe big, issue is that the implied constants again can depend on d. So this is really an asymptotic result as m goes to infinity. Some remarks. No matter what alpha and d are, this means that you can always upper bound the sampling numbers by m to the minus 1 over 2. So this means you don't get a curse of dimension in the sense that as m goes to infinity, this exponent here, or I mean the exponent of m to the minus something, does not deteriorate with d. It can still be that the implied constant here gets quite big, exponentially in d, for example, but at least the rate of decay is independent of d. We can also, for simplicity, I formulated everything here for L2 recovery. You can also do recovery in LP, and then you get this exponent here up to log factors. And this means that if p is very large, the rate of decay again is not very good. So for example, if p is infinity, then this term here drops out and you get m to the minus alpha over d, meaning that then you are again fully subject to the curse of dimension. And what is perhaps interesting, as we will later see, the recovery algorithm that you have to use here, or that comes out of the proof, is nonlinear. And you can actually show that if you want to study the linear recovery algorithm, so the linear sampling numbers, then they are actually lower bounded by m to the minus alpha over d. So in this case, the linear sampling numbers are always subject to the curse of dimension, but these nonlinear sampling numbers are not. And before I go into the proof, starting on the next slide, just two open questions that I am quite interested in studying further. So one is, okay, the implied constants here can depend on d, meaning they can be quite bad. So the question is, what happens in this so-called pre-asymptotic regime where m is not exponentially large in d? So how do the sampling numbers depend then, or behave then? And the second question is these sampling numbers, you can choose the sampling points as you want, right? You are completely free in choosing the sampling points. Whereas for applications, for example, in machine learning or statistics, it's more natural to assume that the sampling points are given to you, maybe by sampling them randomly from the domain. And I don't know what happens in this case. So if the sampling points are chosen randomly and not in a clever way, as I will present in the proof, then I don't know how these sampling numbers behave or how well the error decays. And I think this is also a very interesting question. Okay, if there are no questions, I would now go into the proofs. Okay, in the proofs, they all rely on one very nice result from compressive sensing that probably many of you are familiar with. But for the sake of completeness, I will recall them also because they are quite nice. And this is basically a sampling result from compressive sensing for how well one can recover from point samples a sparse linear combination of a bounded orthonormal system. So the setup is as follows. You have capital N, or you have an orthonormal system with capital N elements, so phi1 to up to phi n in L2 on some probability space, and they should be orthonormal and all bounded by 1. So this is what's called a bounded orthonormal system. And then you prescribe a parameter S, which will be the sparsity, as we'll see in a moment. And then if you choose M to be bigger than a constant times S, the number of sampling points, and the logarithmic factor involving the number of elements in your orthonormal system, then the following holds true. If you choose M sampling points randomly from your domain, then with high probability regarding the sampling points, the following holds. You prescribe any noise level eta, which we'll see in a moment what it does. And then for any function, which is a linear combination of your bounded orthonormal system, but it should be a sparse linear combination. So at most, S of the coefficients should be non-zero. And if you then don't know the function, but you only know yj, so you only know the samples f of xj plus ej, where ej is some noise, which the only requirement is that it's bounded by eta uniformly, then based on these noisy samples, you can actually reconstruct or construct an approximation to your unknown function f, which in L2 error is as good as the noise level up to some absolute constant. So if you just have up to this log factor as many noisy samples of your sparse linear combination of the bounded orthonormal system, you can reconstruct it with L2 error on the order of the noise level. And out of the proof, I mean, this is taken from this very nice book by Holger Rahut and Foucault. They, of course, also tell you exactly how you can get the reconstruction by solving some constrained L1 minimization problem. So this is the building block on which everything will rest, but one still needs to do quite some work to be actually able to apply this result. And we will apply it with this orthonormal system being elements of the Fourier basis. Okay, and what we do for this is we first show that every function in this Barron unit ball allows some kind of Fourier expansion. But the problem is, so we are always on this unit cube here, and our Barron function does not need to be periodic. It doesn't need to be one periodic or ZD periodic. And this means that in general, you cannot, I mean, you can in an L2 sense expand it into a Fourier series, but it will not necessarily converge uniformly, because if the Fourier series converges uniformly, then your function would actually need to be ZD periodic. And somehow to circumvent this problem, what we are doing is we are fixing some bump function phi, which is supported inside the cube and is 1 on this smaller cube, which is shown in green here on omega naught, which is -1/4 to 1/4 to the d. And then you can show that if you take the localized version, f times phi, then this actually admits a Fourier expansion with quite quickly decaying coefficients, meaning that the Fourier coefficients are summable even if you multiply them by this weight here. And I will not go into any details on the proof of this result, I will just say that it uses standard methods from Fourier and harmonic analysis, meaning that if you are somehow familiar in the area, like you know a bit of time frequency analysis maybe, then this is not such a difficult result to get, but it's a bit technical. Okay, now the question is, what do we do with this localized Fourier expansion? We somehow want to use this sampling result here, but for this we need a sparse Fourier series, not just one with quickly decaying coefficients. And what we're going to do to fix this is we will somehow truncate more or less this Fourier expansion so that it only has S non-zero coefficients. But you also need to do that very carefully. So this is the next slide. So we fix some function in this Barron unit ball and some sparsity level S. And then the question is, how well can I approximate F, or at least this localized version, F times phi, using an S-sparse Fourier series? And the claim is there is a Fourier series which is S-sparse. So at most S of the coefficients here are non-zero. And we also know that the coefficients or the frequencies of the non-zero coefficients are not too big. So we know that all the coefficients are zero when the frequencies are this big, like polynomial in the sparsity. And then we get this approximation error in L infinity. So not in L2, but in L infinity. So S to the minus 1/2 plus alpha over D. And this already looks familiar from the bound for the sampling numbers. We get exactly M to the minus 1/2 plus alpha over D. And again, we don't approximate F, but just F times phi. So how do you do this? So from the previous slide, we know that we can expand F times phi into such a Fourier series here, where the coefficients are summable against this weight. Okay. And now we somehow want to basically truncate this, but it's not quite so easy. But there's a very nice result by Devor and Temlyakov, which says the following. If you have such a function here, so if the Fourier coefficients are summable in this sense here, then given any sparsity level S, you can actually approximate this function here, so F times phi, by a Fourier series with only S non-zero coefficients up to L infinity error C times S to the minus 1/2 plus alpha over D. And I was looking for this result for a long time, and when I found it, I looked like this. Because, I mean, so this result at first might look quite obvious or not so deep, but it's actually quite deep because you're doing L infinity approximation, not L2 approximation. If you would be doing L2 approximation, then getting this kind of decay is standard. You just take the largest S coefficients, and then by some Stechkin argument, you get exactly this rate. But the difference is that you get this error over here in L infinity. And if you do the L2 proof, you use heavily that the Fourier basis is also normal, so you have this Bessel bound in L2, and you don't have this in L infinity. So, but still, these two were able to show that you can get a similar result in L infinity. But then you cannot just take the largest coefficients; you need to do something much more clever. Okay, but the problem here with this result is still it tells you there is some S-sparse Fourier series which does the job, but you don't have control over the location of the non-zero coefficients. So it could be that in principle that this involves really, really high frequencies, which we don't want. Okay, but you can fix this problem as follows. Since we have this expansion here, it's not so hard to see that if we just truncate the series taking not too large frequencies, then we get quite a good approximation. And this we somehow want to carry over then to this G here. And how you do this, I mean, this is now a bit for the experts maybe. You use the so-called de la Vallée-Poisson quasi-projection operator. So what you would like to do is just cut off all the frequencies that are too large. But if you do that, you won't get L infinity control. So instead, you use this clever quasi-projection operator, which you know from Fourier analysis that it exists, such that you get L infinity bounded projection operator from L infinity to L infinity. It still doesn't give you too high frequencies, and it preserves all the frequencies up to L infinity norm of the frequency is capital N. And then if you collect everything, it's not too difficult to see that if to this approximation here, you apply this Delavaleur-Poisson quasi-projection, then you get your H, which does this nice approximation here. Okay, now we have approximated our function by a sparse Fourier series. And what does this give us? It gives us the following local reconstruction result. And recall omega is again the full unit cube, and omega naught is this smaller cube inside the unit cube. And now this result tells us the following. If we take s times log to the 4 as sampling points, then we can choose them in the set omega, so in the big cube. And then there's also the reconstruction operator, which then gives us the desired reconstruction error, but only on the smaller subdomain omega naught. So we sample on all of omega, and we only get the reconstruction on the smaller subdomain. Okay, this is the point here. So this does almost what we want, except that it only gives us a reconstruction on the subdomain and not on all of omega. So how do you prove this lemma? Basically, you collect everything that we have seen up to now. Above, we have seen that you can approximate f times phi, so f localized to the subcube basically, by such an S-sparse Fourier series, where you also have control over how big the frequencies get. And then you can basically just apply the result from compressive sensing. So the point is now, if you give me samples f of xi, then I know phi, so I can then compute f times phi of xi. And since I have this approximation here, h is the S-sparse Fourier series, h is very close to f times phi. I can interpret the samples of f times phi as noisy samples of this Fourier series, and then I can use the compressive sensing result to reconstruct h. So using the compressive sensing result, I get an approximation h tilde to h. And then overall, since phi with which localize here is 1 on the subcube, we get the desired approximation result on this subcube. And this is where I was stuck for a long time. So I knew somehow that you could reconstruct by sampling on the full domain, you could reconstruct very well on the subdomain. But I wasn't able to somehow generalize this until I came up with the following trick. So what you do now is, let's start with the interval, right? So you have the interval -1/2 to 1/2. And this you can then divide dyadically. So you divide it into 0 to 1/4. The next interval is half as long, 1/4 to 3/8. The next interval is half as long again, from 3/8 to 7/16, and so on. And then you take tensor products of this dyadic partition of the interval, which gives you then, or which partitions your full cube into a lot of rectangles qi. And the nice property of these cubes qi, or rectangles qi, is that if you take basically twice as large a rectangle with the same center as qi, then this enlarged rectangle still stays in the cube here. This is the first important property. And the second property is, just by an suitable affine map, you can then transform this situation into the situation that we had in the previous lemma, where you basically sample on omega and reconstruct on omega naught. And what this tells us then is that if we can sample our function on the full large rectangle on pi, we can reconstruct well on qi. And since the rectangle pi is still inside the whole domain here, we can do the sampling, which will then allow us to reconstruct f on this rectangle qi. And because we are doing L2 approximation just by a change of variable, I mean, this is not obvious right now, but you can do the calculation, it's not too difficult. You can see that the error on this rectangle qi squared is bounded by the measure of the rectangle times the error that you would get here. And since the measure gets very small for most of the rectangles, then the error is quite small. And then I won't go into the details here, but then you need to carefully choose how many samples do I invest on this rectangle, on this rectangle, on this rectangle, on this rectangle, and so on. And if you do the bookkeeping very carefully, you can see that the full reconstruction error gets you exactly what you want. So somehow what you do is you subdivide your domain such that after a change of coordinates, it looks exactly like the situation from this here, from this lemma here. And then by piecing everything together, you can get the global reconstruction. Yes, and this completes the proof of the upper bound. Yeah, so the proof of the lower bounds, I only will go into it very briefly. So basically what you do is you explicitly construct functions which are in the unit ball of the Barron space, which avoid all the sampling points, but still have quite large L2 norm. I mean, as large as you can make it under the condition that you avoid all the sampling points and are in this unit ball. And you can do this as follows. So you fix your favorite bump function with support in the unicube. And then you dilate it to make it quite small. So to have support essentially of side lengths 1/n. And then you can shift it around, right? So you can shift the support to any of these rectangles here that you want. And it's not entirely straightforward, but also not too difficult to see that the Barron norm of this function is bounded by n to the alpha, and that the L2 norm behaves like this. And then the idea is if someone gives you m sampling points, you choose the side lengths basically as as m to the 1/d. So that you have more, or let's say twice times m many of these subcubes here. And this then means that there is at least one of these subcubes here which has no sampling point in it, which then means that this function here avoids all of the sampling points. And then your reconstruction algorithm can only guess if you took plus this function or minus this function. And this exactly gives you the lower bound for the reconstruction error. And the only thing which I will not go into detail now is if you take a randomized reconstruction algorithm, you need to be a bit more clever. You basically need to choose the position of your function randomly, and then you can show that on average, the reconstruction error will still be lower bounded by m to the -1/2 minus alpha/d. Okay, so let me just give you a brief summary before I wrap up completely. So I showed you what this, how this Barron space is defined, and we are interested in reconstructing functions from the unit ball of this Barron space using point samples. This is what the sampling numbers measure, how well you can do it. And the main result is that you get up to log factors this tight bound that the sampling numbers scale like m to the -1/2 plus alpha/d. The proof was based on this sampling result for sparse trigonometric polynomials, on a lot of approximation theory, and also on some harmonic analysis where we derived that you can actually get this Fourier expansion for your function, and involving, for example, this de la Pousseur quasi-projection operator. Yeah, that was it. I'm happy to answer any questions.
All right. Thank you for the interesting talk. Let's smash that reaction button.